Let's look at an example where we don't have a common base. So remember, our first step is always to get like an exponential equal to either a constant or an exponential. We don't want this 5 coefficient in our way. We should probably move the 73 to the other side. So let's see where these thoughts take us. So I'm going to go ahead and start by moving our 73 to the other side. And then go ahead and divide by 5. So we'll have 10 to the negative 2x equals 73 fifths. So I think we've gotten that in one of our two forms where we either have an exponential equals an exponential, or in this case, an exponential equals a constant. Now pay attention, our constant is not a 0 or a negative, so that doesn't mean this is a no solution problem, right? So let's go ahead and use a method to solve this. I would recommend taking the log of each side. Now it's recommended to either do base 10 or base e, because then if you need to calculate an approximate answer by using a calculator, it makes it easier to do that. Not necessary though. One thing to notice though is we already have a base that's 10, so using a base 10 logarithm might be advantageous because we might actually be able to get our logarithm to cancel out along the way somewhere. So I'm going to go ahead and take the log of each side. So I'll just do base 10, which means I don't write the 10. That's our common logarithm. And then I'm going to use that power property to move our negative 2x to the front. Now, I don't know why I'm rewriting log 10, because log base 10 of 10 turns into 1. So I don't even really need that anymore. And then this is still going to be the log of 73 fifths. You might want to put that in parentheses just to make sure you know the entire thing is the argument of the logarithm. Okay, now we want x by itself. So we'll just divide both sides by 2. So we have the logarithm of 73 fifths, and we divide that by negative 2. So here is an exact answer. Sometimes they want us to leave our answers exact, or if it doesn't specify, leaving an answer exact is always a good idea. In fact, I probably would leave it both as exact and approximate. So now I can throw this in a calculator if I want and get an approximate answer. Putting this in my calculator gives me negative 0.58, but rather than just trusting me, I would say make sure you're getting used to whatever calculator it is you're using for this chapter, for this class in general, and plug it in and make sure that you get that same approximate answer. All right, example 4, we have a problem that is quadratic in form, a quadratic type equation. And that's because you notice we have like the 2 times x here, just the plain old x here, and they both have an e in this term and that term. So that means we can use a substitution. Now, if you remember this from chapter 1, but we're just going to keep seeing this throughout other chapters. We're going to let u equal e to the x. That means that u squared will equal e to the 2x, right? Because it's just taking what we defined u as and squaring it by putting that extra little 2 in there. That's going to make this really easy to substitute u in place of those e's, which then makes this fairly easy to factor and solve. So we need factors of 10, negative 10, that add up to positive 3. So positive 5 and negative 2, let's double check. U times u is u squared. 5 times negative 2 is negative 10. Positive 5u, negative 2u adds up to 3u in the middle. That gives us answers for u, negative 5 and 2. And we are not done with this problem until we've plugged that back into our substitution. So we plug it back in and we get e to the x equals negative 5, or e to the x equals 2. Now let's look at each of these equations individually according to our list and see how they fit our methods to solve. So notice how we have an exponential equal to a constant. For one of them, that constant is negative, and for the other one, the constant is positive. So for the one that has the negative constant, there is no solution. For the one that has the positive constant, we can solve this by taking the log of each side. Now, since the base of our exponential is e, I highly recommend using a natural log because that will make one of our logarithms, at least, cancel out. So there, I've taken the natural log of each side. I chose to do natural log because of the base e. You could still do a regular log, base 10, or whatever base you want, and it would still result in the same ratio and answer. This just gives us a convenient canceling out step. Okay, next I'm doing the power property, or the exponent property, that says I can move the exponent to the front as a product instead. Here's where using the natural log is convenient, because natural log e equals 1, and 1 times x is just x. So we have found our answer. Our exact answer is x times 1, or x, equals the natural log of 2. So there's our exact answer, which is actually not terribly ugly for this particular problem. And then again, if you want to approximate that, that's an easy calculator keystroke, which obtains the answer. It's not negative, I don't know why I wrote that. 0.0693, I don't know how many decimal places we want to list, at least 2 or 3. All right, next video will be on graph.